Welcome to the visit training session titled Severe Weather Applications of the GOES Split Window Difference product. My name is Dan Bicus. Ed Zoke assisted me in putting this together, along with other contributions from Louis Grasso, Bill Line, and Dan Lindsay. For our learning objectives, we're going to utilize the split window difference product from GOES 16 and 17 for the following severe weather applications: identification of moisture pooling along low-level convergence boundaries, identification and tracking of dryline bulges, and identification of convective preconditioning. First, let's briefly discuss the split window difference product, which is the 10.3 micron band minus the 12.3 micron band. Under the condition of clear skies and the temperature decreases with height, water vapor absorbs and re-emits radiation at a cooler temperature. This effect is greater in the 12.3 micron band compared to the 10.3 micron band. Therefore, the brightness temperature at 10.3 microns will be greater than the brightness temperature at 12.3 microns in the presence of water vapor. As the depth of the water vapor increases into regions of cooler temperatures, the split window difference value increases. The case we'll be looking at is from 15 May 2018. The upper left panel is a combined GOES 16 image, which shows both the split window difference product and the IR 10.3 micron band. The linear color table is used for the split window difference product, and the range is modified to -2 to 10 degrees Celsius rather than the AWIP's default of -15 to +15 degrees Celsius, which helps to increase the contrast. One advantage of this product is that it retains color-enhanced cloud tops by combining it with the 10.3 micron band. In the upper right, we have the GOES 16 visible band at 0.64 microns, along with the METARs. In the lower left, we have the split window difference product with the AWIP's default color table called Dust and Moisture Split Window, and the default range of -15 to +15 degrees Celsius. In the lower right, we have the split window difference with a linear color table and a modified range of 0 to 8 degrees Celsius to help improve the contrast of features of interest. The primary feature of interest is an east-west oriented line moving southward that appears in the split window difference product. This is a region of deeper moisture pooled along a low-level convergence boundary and appears due to larger values in the split window difference product for reasons stated on the previous slide. This moisture boundary does not appear in the visible imagery until later in the animation, when we begin to see cumulus along it and eventually convective initiation. This highlights the operational utility of the split window difference product, that under certain conditions moisture boundaries may appear before there are indications of it in the visible imagery with developing cumulus. We switch gears to a different day. This is from 30 April 2019 with the same 4-panel product configuration as the previous slide. First, look at the visible imagery with the METARs, and we can see a dry line moving eastward from eastern New Mexico into the Texas Panhandle, with resulting convective initiation along the dry line and also points further east. If we look at the split window difference product, start with the upper left panel, and we can see that the dry line actually shows up clearly. The moist air mass has large values in the split window difference product, which shows up as lighter or more white in this enhancement, while the dry side of the dry line is darker with smaller values in the split window difference product. Note that the dry line is not a straight line, rather it has bulges along it. This has been noted in observational studies in the past. However, it shows up much more clearly in GOES 16 compared to GOES imagery in the pre-GOES-R era. Under certain conditions, storms may develop at the nose of these dryline bulges due to enhanced convergence, since these are associated with stronger westerly wind maxima. Note how much easier it is to identify these dryline bulges in the split window difference product displays that make use of a linear color table and narrow data range compared to the color enhanced product with a broader range. The diurnal temperature range shows up more readily in the color enhanced product compared to the product with the linear color table, and this may distract you from the feature of interest, which in this case are the bulges along the dry line. Don't be afraid to try different color tables and ranges when analyzing the split window difference product, since there's a diurnal temperature variation in this product. Look to maximize contrast for the feature of interest. Next, we'll zoom into this region to examine the dry line bulges more closely. This is a zoomed in view of the split window difference product and a range of 0 to 8 degrees, like we've been showing in our lower right panel. I'll draw in the dry line bulge. I annotated 2 West Texas mesonet observing sites that we'll look at meteorograms for in the next slide. Note that at this time, Denver City was still in the relatively moist air mass, with a split window difference value of 3.7 degrees Celsius, and Morton is in the dry air mass with a lower split window difference value, as you'd expect. Morton experienced a dry line bulge while Denver City did not. Here are the meteorograms from the 2 sites. I inserted red arrows on the Morton meteogram since that is the time of dry line bulge passage at Morton. Note the rapid drop in dew point and increase in wind gusts at the time of dry line bulge passage. The wind direction also abruptly veers from south-southeast to southwest. The decrease in dew point clearly decreases more gradually at Denver City compared to Morton, which experienced the dry line bulge. This data is confirmation that the features identified in the GO16 split window difference product are indeed associated with smaller scale dry line bulges. Our next case is from 17 April 2019. We're looking at GO16 imagery over southwest Texas into northern Mexico. Upper left panel is the combined split window difference product and the 10.3 micron IR band. Upper right panel is the 7.3 micron band. Lower left is the 0.64 micron visible band. And lower right is the 10.3 micron IR band with METARs. The METARs show a moist air mass here, with much drier and warmer air to its west, and an approaching cold front from the northwest. This dry line shows up clearly in the split window difference product, extending from Texas into northern Mexico. The visible imagery does not show the dry line, as skies are clear. However, there are multiple attempts at convective initiation that seem to be inhibited by a capping inversion. In the 7.3 micron band, note the trend of cooling brightness temperatures on the moist side of the dry line in northern Mexico. This makes sense because the moist side of the dry line would have lower temperatures compared to the dry side of it. However, why doesn't the cooling extend further north or south? To help answer that question, we look at a topographic map. I annotated a segment of the dry line position in northern Mexico. The average elevation of this region is about 2,000 feet and slopes upward in elevation rapidly from east to west. Here's the weighting function profile calculated from the Del Rio, Texas sounding from 12Z. The low-level moist layer extends up to about 850 millibars. The weighting function profile for the 7.3 micron band, shown in magenta, extends down below 850 millibars. However, recall that the region we observed the cooling trend in this band was over higher elevation than Del Rio, thus higher up in altitude and even more likely to be observed based on this weighting function profile. Here's the 10.3 micron IR imagery. Sometimes it's important to experiment with color tables to bring out features of interest. In this case, the cold front is a feature of interest that does not show up in the default AWIPS color table. However, when we modify the color table to bring out more contrast in the warmer part of the color table, we can now clearly make out the southward moving cold front in the animation. We go back to our split window difference and 10.3 micron sandwich product. The dry line shows up clearly. Convective initiation occurs on the moist side of the dry line in northern Mexico, in the same place where we observe the cooling trend in the 7.3 micron imagery. The cooling at 7.3 microns is likely caused by ascending motion at the western edge of the moist boundary layer due to backing surface winds forcing moisture upslope as depicted in the topographic map we looked at earlier. This process can be characterized by convective preconditioning of the environment for potential convective initiation. Another contributing factor is preconditioning at the storm scale, with numerous multiple attempts at convective initiation before it finally occurs. Each of the earlier attempts at convective initiation help to moisten the boundary layer and weaken the capping inversion until convective initiation occurs. Finally, notice the black regions in Mexico. These are regions of blowing dust with split window difference values that are negative. This enhancement is more focused on moisture than dust, so let's compare how this looks in other enhancements in ranges. Here's the same split window difference loop with the same display we just saw in the upper left for comparison purposes. The linear color table from 0 to 8 degrees Celsius is in the upper right panel. The bottom two panels span the -15 to +15 degrees Celsius range, which is key to picking up dust with the negative values. The lower left panel shows dust as brown, while the lower right panel shows dust as purple. These tend to pick up on the dust more clearly than the top two panels. The southernmost blowing dust region develops clouds within the dry air along its leading edge, likely indicating a region of speed convergence due to a strong westerly wind surge. As this region intercepts the dry line, it seems to correspond with convective initiation for the southern storm, with the northern storm being aided by the cold front. The radar reflectivity from the Del Rio WSR-88D prior to convective initiation shows horizontal streets that rotate counterclockwise, consistent with backing winds, which would aid to the upslope flow along the ridgeline where convective initiation eventually occurred. After storms develop, the southern storm in Mexico is isolated and turns to the right of the mean flow, while further north we see rapid evolution to squall line development along the cold front. We switch to a different case, May 25, 2019 in West Texas and eastern New Mexico. This is the split window difference and IR combination product, which shows a dry line in eastern New Mexico extending into West Texas. In West Texas, we see a storm split with a left mover moving due north and a right mover moving off in this direction. Note that the anvil orientation of the left mover is much different compared to the other storms. In the wake of the storm, we see a darker region right in here that looks similar to the cooler region west of the dry line. Is it really drier in this region? No. Note that the region of interest behind the left mover does not move with the mean flow, therefore it's likely a ground feature. In this instance, the soil moisture is relatively dry before the storm, then rain from the storm contributes to increased soil moisture. The signature we're looking at is a soil moisture signature with higher soil moisture associated with cooler brightness temperatures. Note that the storms further to the north along the New Mexico border also have soil moisture signatures in the wake of the storms. This example illustrates potential pitfalls associated with interpretation of the imagery. The key is looking for movement of features and taking the context of the situation into account. In conclusion, this GOES split window difference product has multiple applications that are useful for severe weather events. Be sure to experiment with different color tables and ranges to bring out the most contrast for the feature of interest. The split window difference and IR sandwich combination presented here is available as an AWIPS procedure, which can be downloaded from the store page on the virtual lab at this address. The color table shown in this presentation can be found here, also on the store page. For more information, here are links to a journal article and a FTDT Go's application webinar on the split window difference product.